Okay, today we're going to talk about something called the well-ordering principle. Let me write down for you what that says. Okay, it says every non-empty set of integers that is bounded below has a smallest, actually I would prefer to use the word least element. Okay? So if you have a set of integers and every integer in that set is greater than or equal to some integer, then that set has to have a smallest integer. Okay? Like, for instance, I'm going to write down a set of integers that are all equal to or greater than 5. I didn't say I'm going to write down the set of all integers equal to or greater than 5. I said a set of integers that are all equal to or greater than 5. That's a set of integers, right? And all of those integers are equal to or greater than 5, right? And it's not an empty set. So it is a non-empty set of integers that is bounded below. So the well-ordering principle says that there must be a least element in that set. And it's very easy to find. It's right here. It's the number 6. Okay? So that's not hard at all to understand. In fact, I think the hardest thing about this is understanding why it even deserves to have a name, the well-ordering principle, because you're probably thinking, well, of course there has to be a least element. Just look at the set and find the least number in the set. Okay, but the reason why it's important is because of the fact that this statement would not be true for some other types of numbers. If I replaced the word integers with real numbers, then it would no longer be true. Let's test that out. What if I crossed out integers and wrote real numbers? Then this would no longer be true, because I could write a non-empty set of real numbers that is bounded below, like the closed interval from 0 to 1. That's non-empty, and it's a set of real numbers, and it's bounded below because everything in there is greater than 0. But it does not have a least element, because no matter what number you pick in that interval, I can always find a smaller number. Okay? If you don't believe me, then you can email me what you think is the smallest number in that interval, and I will very easily email you back a smaller number that's also in that interval. So you see, that's why the well ordering principle is important. It's not because it surprises anybody. It's important because it is a special property of the integers that the larger set of real numbers does not have. Even the set of rational numbers, the well ordering principle would not work, but it works for integers. Okay, and I'm going to show you a way that this is useful. What we're going to do is we are going to prove what's called the division algorithm. This is very important in number theory. Okay, it says if a and b are integers and b is greater than 0, then there exists unique integers q and r such that, I like to abbreviate such that with just st. Some people like this symbol for such that, but I don't personally like it because it looks like a backwards element symbol, and I'm just worried that that can cause confusion. So I never use that symbol for such that. I just use st. Okay, such that r is non-negative and less than b, and a equals q times b plus r. Okay, that's the division algorithm. You look at that and you don't see division in there anywhere at all, do you? Well, here's why it's called the division algorithm. Because q is called the quotient when you divide a by b, and r is called the remainder. Okay, so if you have a divided by b, you can find the quotient and call that q, and you can find the remainder and call that r, and you would then have a equals q times b plus r. And you would know that r is non-negative and less than b. I mean, you remember back when you learned long division in elementary school, right? The remainder is always less than the divisor, and the remainder is never negative. Okay, what we're going to do is we're going to prove that this quotient and remainder exist. We're not going to prove that they are unique. That takes a bit more work. And I just want to show you how to use the well ordering principle. And we use that when we're trying to prove that there is a certain quotient and remainder. And I want to do it so that you can see how the well ordering principle works. Okay, so here's what we're going to do. Given a and b in the set of integers, with b greater than 0, let A, capital A, be the set of all numbers a minus xb where x is an integer, and those values a minus xb are non-negative. Okay. I'll do an example with you. Let's see if I can fit this over here. Let's do an example. Suppose, for the sake of argument, that A is 17 and B is 3. Okay, then our set A, capital A, whoops, hang on. Then our set capital A in this point would be this. Let's write down A minus any integer times B. So I'm just going to do some scratch work here for a second. Okay, so there's A, and B is 3. Okay, so if I subtract multiples of 3, I'll get 14, 11, 8, 5, 2, -1, -4, and so on. Okay, now if x is a negative integer, then to say A minus xb will be adding multiples of 3. So I'll also have 20 and 23 and 26 and so on. Okay, and capital A is the set of all of those that are not negative. So in other words, those numbers make up capital A. Okay, so capital A equals 2, 5, 8, 11, and so on. All right, we'll leave that example there for a minute. Let's get back to our proof. Okay, by the well ordering principle, A has a least element. Call it R. Okay, go over to our example there. Can you find the least element? And what is it? It's 2, right? So in our example, R equals 2. Now you might ask, you might say, okay, again, I don't understand why you have to say by the well ordering principle. Can't you just look and see that there's a least element? You don't need the well ordering principle to tell you that there would be a least element. Okay, and that's an understandable claim, but here's the reason why I need the well ordering principle. You see, in that blue example on the side, that's just one example. I can see the least element in that example. I can look at 1,000 examples and I can find the least element in all of those 1,000 examples. But over here, I just have variables. I don't have any numbers. I can't look at this and say, oh, here's the least element, I see it, because I don't. Okay, so I need some sort of a reasoning for me to claim that I know there's a least element there. And that's what the well ordering principle does for us. All right, now let's continue. Okay. Since R is an element of A, and everything in A looks like that, then that means that R equals A minus XB for some integer x. And we're going to call that value q. Call this integer q. Okay? So that means that r equals a minus qb. Which means, by the way, A equals Q, B minus, rather plus R. Just like I was trying to prove. Okay? But I'm not done yet, because I also need to prove this as well. I also need to prove that R is non-negative and less than B. Okay? Well, the fact that it's non-negative is easy because, look, everything in A is non-negative, so that part's easy. But the fact that it's less than B takes a few statements. Okay? So, since R is an element of A, then R is non-negative because everything in A is non-negative. Okay, also, R is less than B because if R was not less than B, in other words, equal to or greater than B, then that means that R minus B is non-negative, and it's an integer. R minus B is an integer because R and B are both integers. Okay, and what else could I say? R minus B would equal, well, remember, R equals A minus QB, so that would be A minus QB minus B, which is the same thing as saying A minus Q plus 1 times B. So look what I have here. R minus B equals A minus an integer times B. So where would R minus B be located? It would be in the set capital A, right? Because it's a non-negative and it equals A minus an integer times B. So R minus B would be an element of A. But what did we say about R? We said that R is the least element of A. So R minus B can't be an A because R minus B is smaller than R. So let me write contradicting the fact that R is the least element of the set A. Okay, so what do we have? We have R equals A minus QB. Well, actually, that's not what I wanted to point out. Hang on. I want to underline the one beneath it. We have A equals QB plus R. And R is between 0 and B. That's what we are trying to prove. A equals QB plus R, and R is between 0 and B. Okay? And there we go. That's the end of the proof. Now, to mark the end of a proof, we will often put a square like that. By the way, in our example over there on the side, what's Q? A was 17 and B was 3. We got R as 2. What's Q in this case? How did we find Q? Look back at this. Here's how we find Q. R equals A minus BX for some integer x, and we call that integer Q. So in other words, we would say this. 2 equals 17 minus Q times 3. What would Q have to be? Q would be 5, right? 17 minus 15 equals 2, and 15 is 5 times 3. So Q would be 3 in this case. And that's, I'm sorry, 5 I mean. And that is the quotient, right? When you do 17 divided by 3, 3 goes into 17 5 times. That's the quotient. And that gives you 15, and the remainder is 2. Okay? So the important thing about that, I mean, the division algorithm is very important. You use it a lot in number theory. But for right now, for our purposes, the important thing is, I want you to notice that I would have been stuck if I didn't have the well-ordering principle, because without the well-ordering principle and without actual numbers to look at, I could not have said for sure that the set A would have a least element. And without that least element, then I wouldn't have R. And without R, I wouldn't have Q. Okay? Now I know when you actually do a division problem, you always find Q first, and then you find R at the end. Okay? But we aren't doing a division problem here. We're just proving that every division problem has a quotient and a remainder. And to do that, we find the remainder first, and then we use that to find a quotient. Okay, that's all for today.